So we are going to introduce test space model with the aid of this mass spring damper system, which when a force F is applied to it, the force have two opposing forces due to the damper and the spring, and applying the force lead to the displacement of this mass with a velocity b. So state space model have two equations, which are the state equation, which model the first order derivative of the states as a function of the state and the applied input, and the second equation is just the output equation, which is also a function of the state and the applied input. So the state vector x is just a set of state variables that describe the internal dynamics as well as the evolution of the system over time, where u is the applied input or input to the system. In this case, we have only one input, which is the applied force, and y are the desired output we want to analyze or control. So this system, which is the mass spring damper system, is a second order system. So we know the order of the system by counting the energy storing components in the system. So this system has two energy storing components, which are the damper and the spring. So in order to fully model the system, we need two states. However, we can use more than two states, but those additional states are redundant states. So the states that we choose for modeling our system using state space model are the displacement and the velocity, which are x and b, and I name them x1 and x2. So from Newton's second law of motion, we know that the force, applied force, is just equal to the mass times acceleration plus the damping coefficient times the velocity plus the spring constant times the displacement. So from 1, we know that S2 is B, which is the first order derivative of the position or displacement, which is equal to S1 dot. Therefore, from 3, S1 dot is just X2. And from 3 also, we know that taking S2 dot will have the second order derivative of the displacement, which is S dot dot. So substituting 1, 3, and 5 into 2, our equation 2 will reduce into this equation, and making S2 the subject of the formula, we will have equation 6. So from 3 and 6, we have our state equations, and we can put them in matrix form in order to obtain this matrix form equation. So this is basically our A matrix, which is also known as the system matrix, and it is a matrix that models the internal dynamics of the system. And this is our B matrix, which is known as the control matrix, and it is the matrix that shows how our inputs, in this case force, affects our states. And U, which is the applied input, is just our applied force. By giving the following system parameters, our state equation will just turn into this, and the output equation now depends on the state we want to analyze or control. So if I just want to analyze the displacement, my y will just be equal to x1, and my output equation will be A. And if I want to analyze both displacement and velocity, my output equation in matrix form will just be B, where my output matrix is just C, and it's just a matrix that relates my output and the state. So as you can see from both A and B, my direct transmission matrix D is 0, because direct transmission matrix is just a matrix that shows how the inputs directly affect the outputs without any influence on the states. And for most dynamical systems, that is not possible. The input affect the output through the states. So now let us go to MATLAB and see how we can implement state space model. So here we are in MATLAB. I've already written my A, B, C, D matrices. So if you want to convert your state space model, you just use the state space, which is SS function, and you just write your A, B, C, D matrices as the argument of the function. And as you can see, the solution will give you the continuous time state space model. Now let us jump to SIMULINK and see how we can achieve the open loop control of our mass spring damper system, and also see how we can visualize our position and velocity with different applied forces. So here we are in SIMULINK. I have my mass spring damper system, which is composed using this test space model block. If I go into it, you can see I have my state space model, you just have to write your A, B, C, D matrices, which I already wrote in MATLAB. And we have the applied input, which is the applied force going into the system. And I have my output, which are 2. So I use a demultiplexer to separate the position and velocity. So I have 2 scopes for my visualization. This one is for visualizing the output and this one is for visualizing the input. So if I go into the input, which is a step input, if I start with an input of 1 and then click on run. So as you can see, at time 1 second I applied a force of 1 Newton and the position and velocity were both 0 until 1 second, and the mass spring damper system started accelerating up to a velocity of 0.07 meter per second, and also it starts some displacement, so it eventually settles at 0.01 meter, which is 1 centimeters, and when it settles the velocity is 0 because it is no longer changing. So applying 100 newtons, you can see now it settles at 1 meters and the velocity also goes to 0 meter per second. So this is just open loop control where I manually applied the forces in order to visualize my position and velocity. If you want to learn how to achieve closed loop control of mass spring damper system with LQR or pole placement, watch the videos on the screen. Please like and subscribe to the channel. Thank you for watching.